So, thank you. Next presentation. So we'll have the new challenges of machine learning in certified system of SNCF. So Cedrick Lelionnais and Phillipe Bourdent.
So, good afternoon, everybody. Before presenting us, I would like to make a short introduction. Machine learning is, as you know, everybody, in many applications, and in many applications, and we can generate with machine learning rules, and those rules generate. It's very difficult today to formalize these rules. So we are going to share you a presentation today about the certification of systems which integrate properties of machine learning.
Next. Good afternoon, everybody. I've joined the SNCF 2 years ago, and I belong to the AI team of the Rolling Stock Engineering Center, in which I'm working on a program of DMI certification using deep learning classification technologies. I'm also working on a human detection program and crowd counting in suburb trains applying algorithms on video protection images.
Next, please. Cedrick Lelionnais. So I worked at the Rolling Stock Center Engineering for 5 years, and I mainly work at the Artificial Intelligence Pole, and I'm involved in research and development on safety use cases. Next. So the context of certification, we have to distinguish today European certification and the certification in the broad sense. Certification in the broad sense comes to cover all the approval process, and in fact European certification is a stage of the approval process. In the European certification is regulated by a directive on technical specification of our interoperability, is delivered by a NOBO, notified body, and at national level, the qualification operational qualification is authorized by the end customer, and in the systems undergo the qualification operational. Next, please. So the challenges of machine learning certification is in line with the VIG cycle, and in fact we could imagine a further adaptation of this cycle for machine learning algorithms when the systems we to integrate these problematics. Next, please. So we have to define properties, and DEAL, which is a consortium which brings together academics and industrials in the field of transport. They currently focus on those properties. They identify 7, and we are going to present you after that a contribution of these properties, 3 of them. It's data quality and then representativeness, the explainability, and finally the robustness. Next, please.
Well, at the Rolling Stock Engineering Center, our team is pursuing a safety equipment approval strategy that remains faithful to the V cycle. We follow the entire industrialization processes by first working on the specification and the launch of the call for tenders to manufacturers. Next, manufacturers design and build their solution and set up a functional validation process to verify and integrate their products. And once the product has been validated, we step back into the operational qualification and integration of the safety equipment in which the product is subjected to interoperability test scenarios. These tests are carried out on a bench for qualification and a test train for an integration part. Finally, once these steps have been certified as compliant, the equipment is authorized for commercial operation. These essential steps already show us how important it is to establish a common language between the stakeholders of a project, right from the specification of a product. Obviously, the aim is to save time on the homologation processes. Integrating V&V concepts in the upstream phase of the V-cycle is more and more required. For example, model by design, model checking, and so on. It's very important to take this in consideration when building an homologation process chain. And this is what will condition our approach for the future work. Next, please. It will be the same with the safety equipment, which will be able to integrate machine learning algorithms. However, the task promises to be very complicated with this type of solution, since machine learning model is difficult to interpret, which is antagonistic to the certification processes, which are based on deterministic approach. Exactly as Stefan said it in a previous presentation, this is a true paradox, because certification is based on causality, and there is no causality principle in artificial intelligence, not at this step. So we must therefore define levels of explainability to first analyze the models that have been designed. And then in the second step, we must define one or more processes which will be based on new evaluation metrics. Machine learning models are increasingly efficient, but are even less interpretable, like neural networks, for example. It was therefore important for us to consider in our approach the detectors that we encounter mainly for the recognition and localization of shapes in the computer vision image.
Next, please. So, it's very important to establish ties between stakeholders. For example, at the functional validation stage, we could highlight a level of explainability to analyze the robustness of the detectors. Our contribution, we currently focus on the relevance, but maybe we can find other metrics. For operational qualification, the view is different because the detector is within the system. So the analyze is on all the systems, and the system has to be put in realistic operation conditions. And the qualifier has to define test scenario in compliance with that. And at the end, we could help the operator too with another level of explainability to assist the qualifier in his analysis. Next, please.
Our approach shows first feedback. Before considering working with a detector, we started to analyze a classification model, which is a neural network, but has fewer layers than a detector. Here we can see an image of a part of a DMI. The classifier, we only assign a class to the recognized shape in an image. In this example, the model in question classifies the pictograms that are found on the drive machine interface in trains. On the upper part of this workflow, the model in question is conventionally subjected to a stage of evaluating its performance based on test data. The metric used for this type of model are so-called scoring metrics, which, among other things, measure precision. The innovation consists in the low-level part of the workflow that we have set up to analyze the model. In this step, new metrics were identified to assess the relevance of the decision taken by the model. The relevance is represented by a mapping of the pixels that have been designated. In our case, these pixels are consistent with the shape which has been recognized, but sometimes outlier pixels can be found and they can bias the decision. So on the next, to go further, we intend to build. Yes, thank you. To go further, we intend to build a detector which, in addition to classification, locates the shape that has been recognized in the image. The architectures chosen for this type of model present neural networks with many layers to first reduce the region of interest and then classify the shape. This use case considered in the study is about detection of trackside signal. At the moment, it is now a work in progress, so we are not ready yet to fetch performance indications, but this is a project. But like for the classifier, the ultimate aim is to define new location-specific metrics. This is the ultimate aim. From these metrics, we'll be able to build a robustification process, as Cedrick shown at the time, to rework the detector by specifying the training dataset.
Next slide, please. So, at the operational qualification stage, the principle is close to the functional validation stage. On the one side, we have detection predictions with scoring metrics. And on the other side, we have the analysis with metrics to assess the behavior of the system. If we take an example, for example, at this stage, the ATO with a signaling detection, test scenario have to be created by the qualifier. And one of these scenarios could be a flashing light and adapting the speed of a train, or the crossing of a stoplight. And so we have to consider the state of the light during all a sequence. So for that, we have a metric like a time integration, but it's not enough, because maybe in worst case, like weather conditions, according to weather conditions, to environmental events, or even adversarial attacks, it's very difficult to be right with the data. So the test data have to be simulate the realistic conditions, and one metric could be imagined for that. It's the out of distribution, in order to be sure that the distribution of all the test data are at the limit of the distribution of the train data. Next, please. Thank you. Sorry. Another level of explainability could be for the certifier who establish the safety rules. So, in fact, we can find that at the end, this the rules modified or adapted could be also integrated in test scenario. Next, please.
So in order to conclude, we have faced these challenges. First, integrate certification process for machine learning algorithms, and then improve reliability in AI approval processes, and then provide explainable AI levels in accordance to the audience. And at the end, our perspectives are to be able to exploit a new API approach to both robustify and monitor detectors, define new metrics of explainability, and define a taxonomy of certification concepts from explainable AI levels.
Thank you for your attention.